Today, we want to continue integrating rational functions. What we should notice at this point is that there are a few calculus things that show up. Then the rest of it is just hitting the rational functions with the algebra stick until we get down to the three or four cases that we need. So let's talk about the things that we need to be able to do. If the first thing that we look at is the degree of the numerator and the degree of the denominator. What we want is the degree of the numerator to be less than that of the denominator. So if the degree of p of x, this is our first stop. If the degree of p of x is greater than or equal to the degree of q of x, then use long division to rewrite the integrand into a new polynomial as a mixed number. Oops. So there will be a polynomial plus another fraction. And in that fraction, the numerator will be less than the denominator. So you'll get a polynomial plus a fraction where q of x is still q of x, but the numerator will be less. I'm going to call it r of x for remainder. So in this case, the degree of r will be less than the degree of, or equal, less than, strictly less than the degree of q. So that was the first step. This is for any size of q and any size of p. If the degree of p is bigger, if the degree of the numerator is bigger, then we use long division to rewrite it in this mixed number format. Next, we need to consider if q of x is quadratic with complex zeros, then we're going to have some combination of natural logs and tangents. So the next thing we look at is q of x. If q is quadratic with complex zeros, if q is quadratic with complex zeros, then we're going to have arctangents and natural logs. So these are two of those cases. If q is quadratic with complex zeros, then we're going to get arctangents and natural logs. Arctangents from the constants over the q of x, natural logs from the linear over the q of x. So arctangents from trigonometric substitution or just knowing, and natural logs from regular substitution, vanilla substitution, not burning crusade substitution. I refer to trigonometric substitution as burning crusade substitution because trigonometric substitution is kind of like the expansion pack for substitution, and it's the best expansion pack for substitution, so burning crusade. Because, I mean, that's just a fact. I'm kidding, that's an opinion. So the last thing that we need is to figure out what happens if q of x is quadratic with real zeros, or if q of x is degree bigger than 3. So that's stage 3. So third thing if Q of X is quadratic with real zeros, if Q is quadratic with real zeros, that is, it's factorable over the real numbers, or if Q of X is degree greater than 2, then we use partial fraction decomposition. So partial fraction decomposition is one of our techniques, algebra. Long division is one of our techniques, just algebra. So the addendum to this, the fourth thing, which is less of a thing, is that if Q is quadratic with complex zeros and Q has an X term, so there's like a 2A, if Q also has an X term, then we complete the square. So this is like a 2A. If Q is quadratic with complex zeros and has an X term, then complete the square. That is, rewrite it from standard form, ax squared plus bx plus c, to vertex form, a times x minus h squared plus k. Then we will definitely be looking at one of the three cases that we had before, integrating constant over a power of a linear function, integrating a constant over a quadratic with complex zeros, or integrating a quadratic linear over a quadratic with complex zeros. So the one thing that we have to look at is partial fraction decomposition, which is what we want to look at today. So let's look at partial fraction decomposition. This is just reverse addition of fractions. So partial fraction decomposition is reverse adding fractions. Partial fraction decomposition is just adding fractions in reverse. So yesterday, we had an example where we were adding fractions. So if I take something like 3 over x minus 2 minus 4 over x plus 5, this is the one that we would want to integrate. But in the integrating rational functions game, the sum is what we will end up integrating. So 3 times x plus 5 minus 4 times x minus 2, and we could pretend we're back in algebra, the good old days of algebra. I don't know if your algebra experience was good old days. It was not good old days for me. This is going to be x squared plus 3x minus 10. And then the numerator is going to be 3x minus 4x, or negative x. And then 15 plus 8 is 23. So when we go from left to right, we're just adding fractions. When we go from right to left, that's partial fraction decomposition. So this direction is just adding fractions. And then in reverse is partial fraction decomposition. So let's think about, let's set up the rules. Let's set up the process of partial fraction decomposition. Right now, we're looking at partial fraction decomposition, not in the context of calculus. We're just looking at this as an algebra process, going from this fraction to this fraction, minus x plus 23 over x squared plus 3x minus 10, to 3 over x minus 2 minus 4 over x minus 5. The calculus part is to integrate this fraction, the 23 and the negative 10, I break it up into these two fractions because integrating these two fractions is simple because it's just a constant over a linear factor. So 3 over, the integral of 3 over x minus 2 is 3 natural logs of a absolute value of x minus 2. And then the integral of the second fraction will be minus 4 natural logs of absolute value of x minus x plus 5 plus c. So the calculus part is not the interesting part. This is what we need to work on, just as an algebraic process. So we're going to be playing the algebra game for a little while, not the calculus game. The hardest part of the calculus is process anyway, is the algebra that's involved, not the calculus stuff. I mean, add 1 to the exponent, divide by the new exponent. There's your calculus. Part, substitution, all that stuff is just reading so that you can add 1 to the exponent and divide by the new exponent. So let's set up the process. We're actually going to start with one that we know. So here's how the thinking goes in partial fraction decomposition. We notice that our denominator is quadratic, but with real zeros. It is factorable over the real numbers. So we notice that the denominator is quadratic with real zeros. We know this because we can factor it. Plus 5 and a minus 2, that's how we'll factor the denominator. So that's what we should do. We notice this because it's factorable, so what we should do is factor the denominator. So x plus x minus 2 and x plus 5. Denominator is quadratic with real zeros, so we factor the denominator.
Professor?
Yes. Yes.
Do you have like a preferred method when you're factoring, like a certain technique?
Nope.
Nope. Oh.
As long as you get to the factors, that's all that matters.
All right.
So so we black box from x squared plus 3x minus 10 to x minus 2 and x plus 5. So yeah, that I don't need that. That would be like up here when I did 3 times 5 minus 4 times a negative 2 and came up with a 23. That whatever happened in my head, the important thing was coming up with the plus 23. So that part is the black box, and that's going to be different for all of us. Y'all are going to have different ways of factoring your polynomials. And if you need to write something down, then go ahead and write something down. That's totally okay. If you're like, oh no, I'm totally pro, I can do this in my head, then fine. That's cool too. You know what I mean? The next part is the setup. We're going to write the decomposition, but we don't know what the key thing here is. We don't know what the numerators are going to be. We are looking for the numerators. So the next part is the setup. We split the fraction that we're trying to decompose, and each term, each factor of the denominator produces a term in the sum. So we're making a proposal. Each factor of the denominator becomes a term in the sum. Each factor of the denominator becomes a term in the sum. Each factor of the denominator, not is. Let's say gives or creates, is represented by. Yeah. So let's say each factor of the denominator gives us a term in the decomposition. All of a sudden, I just disagreed with the way I've been saying this for like the last 20 years. I don't know what happened today. So the thing is, we don't know what the numerators are going to be. The process is going to be solving for the numerators. What we want, if we're doing this, if we're setting these things up correctly, what we want is we expect constant functions to be over powers of linear factors. So we just fill in unknowns. Traditionally, it's capitals starting with A. So A and B are the unknown numerators. Those are what we solve. That's what we're solving for. So A and B are the unknown constant numerators. Those are what we're looking for. Now all we need to do is solve for A and B. At this point, you might be thinking, dude, we are trying to solve for two things, A and B, but we've only got one equation to do it. But that's okay. That one equation will produce two pieces of information that will allow us to solve for our two unknown numerators. All right, let's flip pages because I did not plan this well. If we had a professional teacher, things like this wouldn't happen. We wouldn't have to flip pages in the middle of a problem, but you're stuck with me. So there we go. Let's take a look at what we had. I had factored my new denominator. I'm going to go back. I'm going to include this step. X minus 2 times x plus 5. This was under a minus x plus 23. Then we had our proposed decomposition, which had something over the x minus 2 plus some other fraction with a denominator of x plus 5. We didn't know what numerators would put this together, so that's what we're looking for. So we put constants on top of our linear denominators. We know we can get away with constants because we've done the long division to make sure that the degree of the numerator is less than that of the denominator. That's why we can get away with constants. That's why we want to do that long division first. So the next thing we do is just put the generic one back together and make it look like the minus x plus 23. So we take the decomposition and say, this is what we want the decomposition to look like. We want to add these two fractions to make it look like the minus x plus 23 over x minus 2 times x plus 5. So we just put it together. So I have a times x plus 5 plus b times x minus 2, just getting a common denominator and putting these things back together. But generically, because I don't know what the a and the b are. I don't know what proportion of the x minus 2 and the x plus 5 we need to make a negative x plus 23. So what we get on top is an ax plus 5a. Let's see, let's call this all out. We got ax plus 5a. This is all just going on in our heads, plus bx minus 2b. So notice what we have is we have the ax plus bx. So we have an a plus b times x. I didn't do my color matching that I wanted, but that's okay. We have a plus b times x. And then we have a constant of 5a minus 2b. And this is all over the x minus 2 times x plus 5. The important thing that we notice here, now that we've just added our generic decomposition, what we notice is that I want this fraction with the a plus b times x plus 5a minus 2b all over x minus 2 times x plus 5. I want this one on the right to equal this one that we started with, negative x plus 23. The denominators are all the same. So what this tells us is that a plus b has to equal negative 1. So notice that here, a plus b has to equal negative 1. The coefficient of x on both sides needs to be negative 1. And then the 5a minus 2b, 5a minus 2b has to be a plus 23, because that's the constant. So I'm just equating my coefficients. So I get the equation a plus b equals negative 1. So we get the system of equations. We get a system of two equations with two unknowns. I get a plus b is negative 1. And we also have that 5a minus 2b is 23. The solution to this system is going to be the numerators that we were looking for in the first place. So we need to solve this system however we happen to like to solve systems. Usually students like to solve, especially if I drop just like nice integers on you, students like to start off with an elimination or an addition method and then switch to a substitution method because you like to mix it up. So if I multiply the first equation by 2, I get 2a plus 2b is equal to negative 2. Then the second equation is still 5a minus 2b is 23. And so this tells us that 7a is equal to 21. And so that tells us that a is equal to 3. Once I have a is equal to 3, usually we like to just switch back to substitution and say that 3 plus b is equal to negative 1. And so b is equal to whatever it is, negative 4. So then we take the 3, and we all usually pick the first equation because it's the easiest one. So we take the 3 and we say a is 3, so 3 plus b is equal to -1. So b is equal to -4. Those are the two things that we were looking for. A is 3, b is equal to -4. We usually solve a system by starting off with an elimination. If we have a factorable denominator where the coefficients of x are both 1, we have monic linear denominators, then that's just how it's going to go. That's why elimination is going to be so great. But then we always switch to, we never like do the other, no one ever does this where you multiply by -5 after you have this. You're so close to getting b, people be like, oh no, you know what, -5a plus a -5b, let's just write -5b is +5. No one ever goes back and eliminates the a. But you know, it's okay, works the other way too. You can just take this one. Notice you get the same thing because you'd write a -4 is equal to -1. So a is equal to +3 still. So we still get the same set. There are shortcuts to solving this linear system in this particular context. But this is generically how we go about things. Any questions? There is a shortcut to the linear system. There is a shortcut to avoid the linear system, which involves almost dividing by 0. That makes that particular technique very dangerous. It's kind of like Mace Windu's lightsaber technique. You shouldn't just teach that to like to young people that don't have really good control of their emotions. It's very dangerous. But usually it's the first thing that people go after. And then, you know, you wonder why there aren't any Jedi anymore. I'm kidding. There are plenty of Jedi. As soon as some writer needs some Jedi to have survived Order 66, then you just like, oh, hey, what if I have? Yeah, see, because it's Mace Windu is much too interesting to people who have not just seen the movies, and plus he's played by Samuel L. Jackson, so that's a win right there. To say, oh yeah, he must have survived somehow. He's too cool not to have survived. So kind of takes a little bit of the emotion away from the whole thing. We didn't really lose anything. You know what I mean? It's kind of like when you're playing a D&D campaign, and it's kind of like when you're playing a D&D campaign. Once you get to level 5, death is a lot less risky if you have a cleric in your group, because they're like, all revival. Is that what it's called? There's like the level 3 spell. And someone can be like straight up dead for up to a minute. And then once you get to 5th level, you've got the first one where they can be up to like a day, you know. But really, 5th level is not that high. It should be considered pretty high, but it's not that high. People consider that still low level. And you have access to, like, you know, that's kind of like your EMT. After if the rest of you survive the battle, the cleric survives the battle, they just go up and say, "Ah, been dead for less than a minute, revive," and then you're good to go again. And there's not really any downside to it that I can remember. All right, so there is a technique, and I want to point out that it's a shortcut to get around this linear system. I want you to know that I'm aware of it, and I'm deliberately not teaching you that, because this is the one that you're going to find when you go on to Professor YouTube and say, "Hey, Professor YouTube, how do I do this partial fraction decomposition business?" And they're just going to be like, "Oh, you plug in 2 and you plug in -5," and then there's an audible gasp as you're dividing by 0. It's like, no, 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 just erase the denominator. And you say, "Oh, just take this and multiply, cancel out the denominators, then it's not a problem, is it? Or is it?" But then the engineering portion of our brain takes over and it's like, "Oh, forget it, it works, man." And like, "Oh, woo, we came that close to dividing by 0." My favorite D&D class is Wizard. I don't know, I thought that might have been obvious. For some reason, my favorite D&D class in concept is Bard, but I never mesh with the Bard. I can never get into being a Bard. So I recognize that Bard is an awesome class and it's super fun to play, but the way I have fun with Bards is watching someone else do Bard really well. And I just can't make it work in my mind. I don't know why. It's just a mental block. It's the class that I wish I could play. Although a very close second to Wizard. Here's why I'm biased towards Wizards. Why Wizards? I like Wizards so much. I played a Wizard in a long-running campaign to a high level, and by high level I mean 20th level and beyond. And I got to tell you, being a 20th level Wizard is lots of fun. You are just a solutions manual at that point. So if you think your campaign is going to run to a very high level, be a Wizard. And be an illusionist Wizard, because you now have an answer for everything. You're just a solutions manual. And with the notable exception of Fireball, because every Wizard should have Fireball because it's such a fun spell. Don't bother with damaging spells. Get a cantrip, get Fireball. Don't bother with any other damage spell. Do not approach a battle and think, how can I cause damage to the enemy? Approach a battle and say, how can I rewrite the battlefield so that we can't lose? That's what a Wizard brings to the table.
Oh, okay.
Because you have you probably have fighters to do that. That's my second favorite class, fighter. And if next time I play in a campaign, I'm going to be a human fighter, because it's like all super vanilla. What's the most vanilla thing you can be in Dungeons and Dragons? Human fighter. Ostensibly something that you could be in real life.
Or you have a pyromaniac demon.
Mm-hmm. So, but right now, my favorite class is the one that I'm playing at the moment, and I'm actually not playing at the moment, but the most recent campaign I was in that's on suspension right now, I was playing a Warlock. And I got to tell you, a Warlock with just silent, that can cast Silent Image at will and Mask of Many Faces, which gives you Disguise Self at will. Amazing. So much fun. So if you haven't had a chance to be a Warlock, and you happen to be a Warlock in a Thieves Guild, be it Chainlock, Mask of Many Faces, Silent Image, so much fun. It's just shenanigans on a stick right there. All right. Any questions? So, favorite class, Wizard, super biased. Second favorite class, the one I'm playing right now, which happens to be Warlock. Third favorite class, and tied for second in concept, I just kind of want to be a fighter. And then, yeah.
That's it. I don't get to play D&D enough to the point where I'm like, oh, I want to be something really weird. I'm fine with just the regular things that are available. So I'm fine not being like, I don't have to play a ghoul monk or something like that. I don't need the weirdness. You know what I mean? Anyway, it's a good thing it's Friday and we're finishing up. We're going to finish up our integrating rational functions business on Monday, because what happens if we don't have linear ones down here? What if we have a quadratic with complex zeros, so I can't break it down? Actually, I'll just tell you right now. I know we're in overtime, but if the denominator is quadratic with complex zeros, then you don't just put a constant on top, because we saw in the basic ones that there might be a linear on top. So also, if you have a cubic, here's just a short version. If we have a cubic, then you break your cubic down into a linear and a quadratic. If you're worried that you won't be able to do this, you have to be able to take a cubic into a linear and a quadratic. You cannot have a cubic that won't factor into a linear and a quadratic. Your linear might have an irrational zero, but that's still real. The cubic has to have at least one real zero. So pull that one out and then use partial fraction decomposition. And the numerator, oops, we should note that this is the numerator after we've done the long division. This, you have to be able to do this. Cubic has a real zero. So I'll be able to separate off the linear factor and a quadratic factor, and then I can use partial fraction decomposition. If the quadratic will break down even more, then I have 3 linears. If the quadratic has complex zeros, then I have an answer for that. And now we have an answer for every rational function. We just need practice on the algebra that's involved. Notice, no calculus today, except for the fact that I keep saying integrating rational functions, but really, long division, complete the square, partial fraction decomposition, those are the algebraic techniques we use to integrate rational functions. All right, that's going to do it for today. Everybody have a nice weekend. I'll see y'all on Monday, and we'll do a couple of examples of a couple more examples of partial fraction decomposition. I have a D&D game that I'm DMing on Saturday, so I have to figure out. I got a plan for what my players are not going to do, because I'm like, here, they said they were going to do this last week. And they're like, hey, I got an idea. What if we did this instead? Michael, because that's what causes dragons to attack. High-level dragons. That's what burns down towns. When the players are like, we're going to go to point A. And I'm like, great. And I spend a week thinking about point A. Then they're like, you know what? Instead, we're going to go to point B. Because you know what's at point B? Freaking dragons, man. I'm just kidding. You just got to improvise. All right, that's going to do it for today. Everybody have a nice weekend. I'll see y'all on Monday. And thanks for playing.
All right.